Hello, I'm delighted to have the opportunity to present some of our recent work, albeit in a remote pre-recorded fashion. And I'm going to be talking about topology and energy balance. So what is it that we're talking about? Well, one of the key themes of our research group in recent years has been the characterization of contact angle, the angle with which two fluid phases hit the solid. And if we've got a three-dimensional pore space image, we have developed automatic methods to estimate that contact angle value. Now that looks great, but there are two major problems. The first one is that at this three-phase contact in an image, we have to segment between the solid phase and the two fluid phases. And it's exactly at that three-phase contact line that our image analysis is least accurate. So our contact angle estimations have a wide range because of uncertainty. And sometimes there's a feeling that we're tending actually to see contact angles on a voxelized image that tend towards 90 degrees. So the first thing we're going to talk about under topology is there another way of getting at that contact angle without having to look at that three-phase contact point in such detail? Well, here's the idea, and bear with me for a few minutes because it might seem, well, sort of where's it heading? But let's start with something we all know, which is I take a triangle, or indeed any two-dimensional shape, and if I look at the external angles, okay, if I look at the external angles, I think you can see, and you probably did this at school, you go round in a circle. So in fact, for any polygon, the sum of the angles is 2 pi. Okay, so fair enough. So what? Now let's imagine instead that of having a shape that's entirely, straight lines and angles, we actually have a shape which has some angles, but also is curved. So imagine instead, in this example, right, we had a shape that had some curvature like this. Okay, so it's no longer got sharp angles. Is there something else that we could say about going around that shape? And the answer is yes, because we still have these steep angles here where there's a distinct contact, but in the smooth regions, what we can do is we can define a radius of curvature and then a small increment that we might move around this small surface. And what we know, that if we integrate the angle that we move round plus the sharp changes, again, that moves us round into a circle. So we can define a curvature that's 1 over the radius of curvature. And then we can define here the sum of the angles plus the integral of the curvature as we go round the smooth regions. That equals 2 pi. So now you're beginning maybe to see where we're heading here. You might say, I can see it. What you're going to do is you're going to consider this is one phase, say a drop on a solid surface, and from the curvature integral, we can find the sum of the angles because we know they add up to something. Okay, that's sort of the idea. And then the idea is, oh, right, we just integrate over a line or a surface. That's a much more robust thing than actually trying to find these angles directly. So we use this equation and back out the angles, and that's going to be related to the contact angle. But of course, just a minute, hang on, this is two-dimensional. we're in 3 dimensions. So is there an equivalent relationship in 3D? Well, there is. It was first developed actually by Euler, and he described it as a remarkable theorem. And it's this. I take a shape, and imagine this is a sphere, then what's the corresponding integral that ends up with something that's an integer times pi? Well, what we have here is not the integral of the curvature, but it turns out it's the integral of what's called the Gaussian curvature. So we can define in 3 dimensions a curvature in 2 orthogonal directions. So we actually have 2 curvatures on a surface in 3D. So we've got what we call kappa 1 and kappa 2. The Gaussian curvature is defined as the product of those 2. And what you find is that the integral of the Gaussian curvature is equal to 4 pi over the surface. So the integral of the Gaussian curvature over the area is 4 pi. Now let's think about this. If this is a sphere, the radius of curvature is r, the curvature itself is 1 over r, the Gaussian curvature is 1 over r squared, the area of a sphere is 4 pi r squared, 1 over r squared times 4 pi r squared equals 4 pi. Okay. But now, why am I nervously playing with this ball of plasticine? Now it's not a sphere, is it? In fact, it's got all sorts of lumps and bumps. Still has a curvature. Yeah, the integral is exactly the same. So it's the 3-dimensional version of that 2D. Yep, I can integrate this. That's what's remarkable about it. It doesn't matter as long as I don't change the topology. If I do, if I, for instance, put a hole in here, I actually change the topology, and actually now the integral of the curvature over the surface is 0. So in fact, in general, this is 4 pi times chi, which is the Euler characteristic. Okay, well, that's fine, but that's not quite what we wanted, is it? Now let's think about what's going on if we have a case where, say, rather than this nice picture here, right, we've got a more complex 3-dimensional object, and we're trying to understand now wettability. So we can imagine that we have a solid surface and we have a blob of 1 phase, right? And we're going to call it phase 2. Think about oil, surrounded by another phase, phase 1, and that's going to be your water. And we're going to try and use this concept, right, to determine contact angle. So let's see how that might look. Okay, so we've got the solid here. Okay, and then we can imagine that we have a blob of another phase. Okay, and I'll do that in yellow, something like this. Okay, and this is going to be phase 2. This is phase 1. The contact angle is actually traditionally measured through phase 1. So actually this will be the contact angle. Okay, and we can imagine a surface here. This is your solid. Okay, and then we can imagine this in 3 dimensions. So there'll be a 3-phase contact line. Okay, well that looks fine. So really what we want is we want the integral over this surface, okay, the Gaussian curvature, and then there's going to be some contribution of the contact angle, and we know that that should equal 4 pi. Okay, that looks good, but there's a subtlety. And imagine we had a case that actually doesn't quite look like this, but where the solid surface isn't flat. So if we have a case where the solid surface is not flat, then we can imagine, for instance, that the 3-phase contact line sort of goes around more or less in this horizontal plane, but the solid itself is not completely flat. And that leads, unfortunately, to a complexity here. So you can imagine a solid that does whatever you want it to do, but eventually this comes down more or less to this point. So we have a solid that's sort of, you know, doing this. So we still got our contact angle, but we have something else. We have, in the plane of the contact line, the solid is oriented at some angle. So the solid, we can imagine a blob on a surface, okay, a blob on a surface, but the solid is oriented at an angle to the three-phase contact line in 3 dimensions. Now, the problem with that is that the contribution to the curvature at this discontinuity, because that's where the fluids lie on the surface and there's a distinct angle, the contribution to the Gaussian curvature of this depends on the orientation of the solid to the three-phase contact line. And that's a bit difficult to explain, but here, imagine instead of a sharp interface here, I replaced it with a little piece of a torus. Right, so the sharp interface is actually just curved, and then I look at the contribution of curvature, and then it should, you know, relate to this equation here. The problem with a torus is, if you think about it carefully, the total integral of the Gaussian curvature is 0 in this case. If we're at the top, it's flat. Actually, there's one curvature that's 0, so the Gaussian curvature is 0. So at the top and the bottom, the curvature is 0. If I'm here on the outside, it's bulging out in both directions. So here the Gaussian curvature is positive. On the inside, it's bulging out in one direction and it's twisting in. The Gaussian curvature is negative. So the Gaussian curvature changes depending on where you are around the ring. So the contribution to Gaussian curvature of this discontinuity depends on how it's oriented. So it's not as nice as we'd like. There are a number of ways of looking at this. It's Sun et al., Ryan Armstrong's group, that first identified this as something where we could look at contact angle. I've been working on it. I've worked over the summer with an MSc student, Luke Kearney. Maybe the most elegant way of looking at this is we consider a single meniscus. So we consider a single meniscus. It may actually touch the solid in a number of places, in n places. And then what we can derive is a relationship like this. It's topologically actually like a sphere, so it's just 4 pi. This is the integral just over the interface between the 2 phases, just the fluid interface. And then we have another term here, and I'm not going to show the derivation. Is this additional contribution due to the discontinuity can be written as 2 pi n, where n is the number of contacts. So we can have an interface that, for instance, hits the solid here as well. So we have more than one contact line, or one contact loop, 1 minus cos, and you'd like it just to be cos theta, but it's cos theta minus phi. So rather than evaluate theta directly, we evaluate this integral. We've got 4 pi, and we can back out. The problem is this phi. We can try and estimate phi from the geometry. We can assume that on average it's close to 0. I'm going to show some results a little bit later. But that's basically the idea of topology. We're still working on it, but it is rather beautiful that we use this quite basic theorem of topology called the Gauss-Bonnet theorem, and we can then back out a contact angle without directly having to measure it, just from an integral of curvature. So that's idea number 1, but it's still not ideal. And the reason why it's not ideal is that we know this. We put, say, oil or other organic substances into a porous medium, the wettability changes. If we look at the contact angle at any one moment, that's a contact angle sort of at rest. And for instance, phase 1 to advance over phase 2, we may need an even larger contact angle because this is an altered wettability surface. So when we're looking at the dynamics of displacement, the contact angle at rest when we take an image, even if we can measure it super precisely with infinite resolution, all right, doesn't matter the rigor of our topology, it doesn't represent the contact angle for an actual displacement. And that's what we want to know to characterize displacement. And that's also what we want to put in our models. So is there another way of calculating the angle when an actual displacement occurs? Well, the problem there is that a displacement at the Pore scale occurs at sub-second time resolution. So we're unable to see it directly from an image. So is there another approach that allows us to infer it and also that gets rid of, trying to fiddle around with angles? So that's part 2, energy balance. So let's look at energy balance. The idea of using an energy balance to define wettability or to analyze displacement has been around since Norm Morrow 50 years ago. What's new is not so much the mathematics, but the fact that all the terms can be measured from our pore space images. Now, for some of you around last year, you might say, oh, old hat, I'm afraid, Martin, didn't you present this last year? Indeed I did, but now I've got my blackboard, I'm actually going to derive it and extend it. Okay, so, a bit of teaching here. So we imagine, right, say a region of porous medium, that's the solid, okay? And we've got phase 1, which you can identify with water, displacing phase 2, okay? And phase 1, if it's, imagine it's the wetting phase, we have something like this, we're going to have a contact angle here, theta, okay? Now, let's imagine a displacement. So we might not actually see the displacement, but we want to find a contact angle consistent with the change in energy. Okay, so what happens? Phase 1, say, displaces phase 2. There is a displacement. So we move from here to here. Okay. So what's the energy we put in? Oh, it's PdV work, isn't it? Again, standard physics. So the work I put in injecting fluids so that one phase displaces another is good old PdV. Now here we've got 2 phases. So PdV is in fact P1 dV1 plus P2 dV2. And these are the change in volume, right, the 2 phases. But if one displaces 2, then this is minus dV1. Okay. I can then define a capillary pressure, which is 2 minus 1, oil minus water, not the other way around. Otherwise, you're going to get your signs all messed up. Okay. So it's the capillary pressure is P2 minus P1. So if we look at this, this is minus PC dV1. Okay. So that's the mechanical work we put in. Let's, we can play with that. If we're looking at volumes, we can do this directly just looking at an image and we see a change in volume by adding up voxels, but we normally sort of think about it conceptually in terms of saturation. So if we have a porosity here, we have a total volume V, that's the pore volume. The change in volume of the phase will be this dV1 can be written as the total volume times porosity times the change in saturation. Okay, it's just a way of thinking about it. Okay, that's fine. What about PC? Aha, we can use the Young-Laplace equation. The Young-Laplace equation says that the capillary pressure is your interfacial tension times curvature. Now, which curvature do we mean here? This is the sum of the curvatures, not the Gaussian curvature, but the sum of the curvatures. And this curvature, as we've already sort of hinted at, we can measure from our images. So we can write this equation here, our mechanical work is minus sigma kappa phi delta S1 times the volume, sorry, not V1, total volume. Okay, so that's the energy I put in, but that's got to be converted to interfacial energy, hasn't it? So let's look at that, and maybe let's use this part of the board. Okay, so what's the change in interfacial energy? Well, we've got an interface between the two phases. Okay, so we can write there's going to be a change in interfacial area, which is going to be the interfacial tension, which is really just energy per unit area, times the change in the area between the two phases. So this will be the area A12 is this area of the meniscus. But there's also, we've got phase 1 here has replaced phase 2, and here we've got the solid. Okay. So here we've got an interfacial tension between phase 2 and the solid and between phase 1 and the solid. Okay. So we've also got, we've added phase 1, so sigma 1s, and we've taken away phase 2, 2s, and that's got to be multiplied by the change between the area between phase 1 and the solid. Okay, so we've got to relate that to this. Okay, fine. Well, now we've got these pesky interfacial tensions here. Aha! Let's use not the Young Laplace equation, but the Young equation now, because for those of you who know this, right, there is a force balance here. Right, these can be viewed as real tensions. Sigma 2s is equal to sigma 1s plus sigma cos theta. So sigma 2s minus sigma 1s is sigma cos theta. This is the other way around. So this actually can be written as sigma delta A12 minus sigma cos theta delta A1s. This is looking good. And now we can write this. We've got volumes here. We normally write interfacial areas as what's called a specific interfacial area. So it's the interfacial area per unit volume. So we can write this as a little a times v. We can write this as a little a times v. I'm sorry, things get a bit messy. So what we can do now is that this, okay, is equal to this. Okay, conveniently now written down. Let's not confuse the issue. Let's get rid of that. So we can get rid of the volumes because it's all now per unit volume. That's rather cool. The interesting thing for two-phase flow is the interfacial tensions also cancel out, because it's true that basically interfacial tension comes into all the expressions. And now what we can see is we're going to get our final equation. Okay, let's put this on this side of the board and this on this side, and we get our final expression, which I can write out nice and boldly. We've got delta A1s cos theta. That's this term. Put this one over there. Is kappa sigma delta S1 plus delta A12. Okay, and that's our main result. Okay. Now, and the beautiful thing here is these are areas and curvatures and saturations from volume. We can measure those directly on a pore space image, okay, and back out the contact angle. So we have two bonuses with this approach, is that one, we don't actually have to look at the angle itself, and it's the angle for a displacement. Does make one big assumption. There's no viscous dissipation. We assume that in the displacement, no energy is lost because the fluids move rapidly and sort of oscillate around and come to a new position of equilibrium. Seems like a bad approximation for some drainage processes, but for most of the imbibition or the water flood processes in a mixed wet medium, actually turns out to be a pretty good approximation. And as you've seen in the previous talk and in talks later today, we're going to find that actually this so-called thermodynamic characterization of wettability has been really very powerful and has really moved on our analysis efforts. So you might be saying, Blackboard, goodness me, where's the PowerPoint? So let's have a PowerPoint, shall we? So I'm going to just show a couple of slides to finish. So the first thing is just a way of recognizing the people I've been working with here, right? It's not just my work. So Luke, as I said, has worked on the topology, right? There's Lewis. Takashi has worked a lot on the analysis in comparison against simulation. And Abdullah and Alessia have worked on three-phase flow, which we will end with. So using the topology, here's our equation again. We've taken simulated images, so we actually know what the contact angle is because that's what we put in. Okay, and those were Takashi's lattice-Boltzmann simulations. And here is what we put in and what we measure from topology. If we assume that this orientational angle on average is 0, it's not too bad. It is improved if we estimate this orientation angle. So this is looking pretty positive in terms of looking at both the BPAC and the Bentheimer simulations, but there's still a lot of work to do on this topological analysis. For three-phase flow, the beautiful thing, and this is what we've done that's new, is you can actually extend this to an arbitrary number of phases, and it is mathematically elegant. I'm not going to go through the details, but this is the final expression you end up with. And here are these other expressions related to three-phase flow, and they do have an elegance all of their own, which if you're interested, you can read the paper. So let's apply the theory. We did this last year, looking at a water wet and mixed wet medium and coming up with contact angles that seem to make reasonable sense and being very useful in our modeling. And if you listen to Sir Jad's talk, to show how the input of these angles as an initial guess actually enables us to give very good predictions. We've extended it to three-phase flow, a paper hot off the press this year. Here is the equation in all its glory, and in fact, even there, I can't see it all. Okay. What we find in a water wet case, the contact angle between oil and water is 48 degrees. Okay, controversial. It's a spreading system, so this is gas oil. Phase 3 is gas. So the gas oil contact angle is 0, and of course that means that gas is also non-wetting to water, right? The gas water contact angle. But when we alter the wettability, right, we find that the oil water contact angle is now well above 90 degrees. We find that the gas oil contact angle is not necessarily 0, but still gas is non-wetting to oil. But this is the intriguing thing. The gas water contact angle is greater than 90. We can actually show from this thermodynamic characterization that gas is intermediate wet. It's water that's the non-wetting phase. And that is consistent with the displacement, the measured capillary pressures, but the geometric angles give you rather more ambiguous characterization. So it enables us really to pin down what's happening in three-phase flow. And Abdullah later will be talking about this in more detail. So here are the conclusions. We use concepts in topology and energy balance to derive 2 expressions for contact angle. Obviously, we need further work, but for those of you who are mathematically inclined, here are the equations again. So I'll finish there. I hope you appreciated or didn't mind the slight change in style with the Blackboard. And now we'll move on, obviously, students and postdocs who've really done all the hard work this year. So thank you very much.